So in this case, we are going to consider a typical exam revision, which is actually important as you are to consider your revisions, preparations for your exams, as we have covered or worked out the formulas that are needed in your syllabus, as we are going to be having your AC machines for the synchronous machines. So the first question, this is actually November 2023 exam that we are going to be working on. On 4.1, you are given to explain what is meant by distribution factor of a synchronous alternator. What is it that you're supposed to consider by the what? The distribution factor. All right. So remember, our distribution factor, guys, is simply the ratio of the actual EMF obtained. So this one, it is the ratio. Let me just write, but I think I wrote this one on the introduction. So it's the ratio of the actual EMF obtained. So I'm not gonna rewrite these definitions again, by guys, for anything that we did. All right. EMF obtained to the EMF that would be obtained, remember, if all conductors, right, if these conductors were concentrated in one slot only. All right, if all conductors were concentrated in one slot only. So this is what we consider, that they must be now taken into a single slot only. So that is for 3 marks, guys. 4.2, we are given the following information applies to three-phase star alternator. So let's see which information, this whole part. So it's three-phase. So this is for a three-phase, right? We are also given that it's what? Star connected. Star connected. Remember the condition of a star in terms of the line EMF and the phase EMF. So you're given the open circuit terminal EMF. I said whenever you're given this, unless stated otherwise, that is your line EMF. It is a line value that you are working with there. You are given a line value. So we are given EL, which is 3,300 volts. From there, we can have the phase value, knowing that you are in a star. Remember, in star, it follows that the phase value is equal to the line value over what? The square root of 3. So we have the line value. So therefore, we're going to calculate the phase value, our induced EMF per phase. So that was going to be 3,300 over what? Over the square root of 3. So that was going to give us 1,905.256 volts. It is important for you to just know this, guys, as you are given information. We have got the frequency. In this case, we have got the frequency. We also have the speed. As we can see, we are not given the number of poles or the pair poles. Remember, I said from these two, we can have what? The pair poles. Actually, it's like we did a question which is exactly like this. It was exactly like this, but it was, the information is just a little bit. But anyways, guys, let's see the revision. Remember, I said from N, which is equal to 60F. Remember, our N is supposed to be 60F over what? Over P. We can calculate the pair poles. We ended up with cross multiplying. So it will be Pn is equal to 60F, you divide by P. So that's 60F over, you divide by N, sorry. So that is for the what? Pair poles. So you can even calculate those pair poles. So that's 60 times the frequency, which is 50 over what? The speed, and rest per minute, which is 1,000. So we're going to obtain our pair poles, which is 3 pairs. And from there, we can calculate the number of what? Poles. So therefore, number of poles. Remember, pair, we are dealing with two things there. So it's 3 times 2 to have the exact number of poles, which is what? 6 poles. So the way I'm looking into this question is like I did a similar question like this. I think it was on membership. So anyways, but let's see. Let's just consider our question, guys. So that is the number of slots per pole per phase, our N. All right. We are also given that N, which is what? 4. So there we are talking of what? Slots. The number of slots per pole per what? Per phase. No problem. The coil span is 150 degrees. We are given exactly the angle. Remember your coil span from the what? From the pole pitch. The whole pole pitch here is what? Is equivalent to 180 degrees. So we have the part of our coil span, 150 degrees. What is remaining is what we need. Out of the 180, that is the angle of short chord. So that is the condition in this case. Out of 180 electrical degrees here, what are you going to have? So it will be 180 minus 150, which is going to be what? 30 electrical degrees. So from this statement where we are given the coil span, what are we having? The angle of short chord from there. So we are having the angle of short chord instead. So our angle of short chord was going to be what? 30 electrical degrees. 180 minus 150. That is the condition that we have. Okay. Then also the useful flux per pole is given 55 milliwebers. That is what we have. So with this information, the question was taking all these that we have, calculate the possible number of conductors per slot. Number of what? Conductors per slot. This is the part of our question. How are we going to end up with this number of conductors per slot? So if we consider like this question, guys, I talked about a very, very similar question like this. So I'm not going to talk much. Make sure that you go through the videos. I think it is supposed to be example number 2. Yes, example number 2. It's just similar to this one. So with this information, all right, we need the conductors. All right, so let's have it here. Conductors per what? Per slot. So to have conductors per slot, definitely as we can see, to have per, I said you must have this in total. So you must have total number of what? Conductors over this also in total, which is what? The total slots. This is what we need. Are we having the total conductors? We do not have. So this one, we're going to circle it. We do not have it. Are we having the total slots? We also do not have this. So we're going to circle this one also. So this one is going to contain a lot of things, a lot of formulas. I talked about this, our previous example. It was like this. So this one is going to take us a lot of things. So let's focus on the total slots. We do not have that much on the total slots because if we check properly, there's a statement that consists of the slots. Guys, whatever that you need in total, find a statement which consists of that part. Total slots. Total. So in this case, for you to have the total number of slots, in this case, for us to have the total slots, there's a statement which consists of the slots here. It's there. Slots. This is what we need. There's a statement that consists of the slot, but we must get rid of these per value, per pole, per phase. We must get rid of these two, per pole, per phase. So how do we get rid of per? I said to get rid of per, you multiply by that per. So the total number of slots was simply going to be calculated from n times. We want to get rid of what? Per pole. So you must calculate multiply by what? Total pole. All right, which is total number of poles times what? Per phase. We must remove that per phase. Number of what? Number of phases. That is the condition. Number of what? Phases. You multiply to remove this pair because already a statement which consists of slots, these slots, this one, the slots, you must go back to where it is written, where it is involved in your given information, provided it is given. In our case, we have that part. So we are gonna just remove those per pole, per phase, per pole, per phase by multiplying by those. So that is the condition. So our n, all right, before we substitute, do we have the total poles? All right, this is the one that we calculated from that speed and frequency. So you see the importance of this part, guys. So we have this one. This one is already the one that we are given. Number of phases already, we have this. So everything is there. So you're going to substitute our n, number of slots per pole per phase, which is what? Which is 4. Remember, the n is the one that we need to remove those pair. That is the part that carries our slots. So that's 4 times the total poles. We calculated this, which is 6 times number of phases. Remember, it's a 3-phase. We calculated this. So multiplying this, we were going to have 72 slots. Guys, it's like I did this question the way that it is, like as it is. All right, no problem. Let's just do it. So that is the total what? Slots is there. All right. So we've got our total slots there. We now have it. So let's focus on Z total. The total number of what? Conductors. Guys, just for the sake of, you've got a lot of things. Let me just remove this and write answer only here because we have a lot of things. So we said what? Total slots. Sorry for that. Total slots. Know how you calculated this. So we have 72 slots. All right, we calculated this just for the sake of what? The space. There's a lot of things that we're going to need. So the Z total is needed. Total number of conductors. Let's figure out. So for the total number of conductors, we said we need a statement which consists of conductors so far. And there is no statement so far which consists of conductors. The only part that has conductors, which is not given here, is the conductors per phase. Conductors per what? Per phase. All right, just gonna write in what? In short, guys. The conductors per phase. That is the only part which has conductors. So meaning to say, remember conductors, we are saying conductors, guys, per what? Per phase. I want you to see here. Per phase. Per phase. As we need these conductors. So to remove this, we must multiply by what? Phase. So meaning to say, if I have that ZP, which represents what? The conductors per phase. If I have this, I simply need to multiply by what? Phase, the total number of phase, to remove this pair. Remember, we need to get rid of pair so that we remain with what? Total conductors. So we're going to multiply by what? Number of phases, the total, which is number of what? Phases. So this is the formula that we're going to need. Number of phases is there. But we do not have what? Conductors per phase. It's not there. So the question now is, how are you going to find that conductors per phase? Because it's not there. So you see, how do you connect your formulas? You do not have conductors per phase. If we have, remember, the turns per pole. Turns per pole. Originally, it is what? ZP over what? Over 2. Turns per pole concept. So ZP can be calculated if we make the subject, guys, just what? Cross multiply. So it means ZP was going to be equal to what? If we just cross multiply here, 2 times what? It was going to end up as 2 times TP. That is what we are going to have at the end. So this is the formula that we are going to need. But look, we do not have TP. We circle it. Where can we have TP? Turns per phase. Is there a statement that has got something about tens? Nothing here. A statement that has tens. The only statement that has got the tens per phase, but it's hidden inside of it, it is this one. Your induced EMF per phase. It carries this TP, but it's hidden. Remember this. So this is how you find this. Let me just write my formulas, then we just reverse them together, guys, all right? So from what? From EP. Induced EMF per phase. Remember, EP from our formula, we said our EP is 4 times frequency, the useful flux. There we have our TP. All right, our form factor, our pitch factor, our distribution factor. So as we need what? The TP from there. So from there, we can make our TP the subject, meaning to say TP was going to be given as what? EP over all these 4F, all right? Useful flux, KF, KP, and KD. This is what you're going to have. But on this information, the only thing that we have, okay, not the only thing, let's list what we have. EP, remember per phase, we calculated this phase value because we knew that we are in what? In a star. So we have this value already. It is calculated. So we have this value. The frequency is already given. Useful flux is given. We are not given the value of the form factor. We are not given the value of the form factor. I said if you're not given, you use it as what? 1,11 in every case. So we have this value. If it is not given, you use the form factor as what? 1,11. Your pitch factor, you do not have. Totally, there's nothing. You have to calculate it. The distribution factor, we do not have. So what are we going to do is to calculate these two. Guys, take note. We are going to what? Calculate. Let's finish up. We are going to calculate KP and KD. We substitute them here. We find TP. After finding TP, what are you going to find? After finding TP, we can find ZP. After finding ZP, what are you going to find? We can find our Z total. We are now reversing up to the question that we are given. So we are going to calculate this and reverse your formulas and reverse up to the question, up to the question. Up to the question. So we're going to reverse our formulas up to the question. After this, we're going to come back, we substitute, we find TP, we find. So this is the case. We just need these two. That is where where we are going to be stuck. So what about KP and what? And KD. These ones we can calculate. We've got formulas. So let's calculate these two. So that is the idea, guys. This is how you answer your exam. So KD, KP and what? And KD. Our pitch factor and distribution factor. So remember, our pitch factor can be calculated out of the pitch that we have. Remember, we have got cos of the angle of short chord over what? Over 2. And we have the angle of short chord, 30 degrees. So here's just a substitution. That's 30. Remember, guys, having your information is important. You see, if you have information, you just substitute. So that's cos what? Cos of 30 over 2. Like this one. So that was going to give us 0,966. Guys, it's like I used these values as they are in a previous example. I'm not sure, but no problem. All right. So we've got our pitch factor, our distribution factor. Remember our distribution factor, like I said, you can use the formula that you're given as it is in your formula sheet, or you can use the sign of n. Then we're going to use gamma in this case over 2, which is our slot pitch that we have. N, the sign of what? The slot pitch over 2. So you can use alpha there, right? Your slot pitch. So N is already there. Remember, N here, our slots per pole per phase, they are already there. But we do not have what? The slot pitch here. So we are going to need our slot pitch. So depends with the symbol that you're given in your textbook. All right. So where can we have the slot pitch? Remember, this is taken from a formula. You're supposed to use the formula direct from the what? The concept of the pole pitch out of what? Out of 180 electrical degrees. I said we can calculate our pole pitch from there. 180 degrees, electrical degrees over what? The slots per pole. So in this case, we are going to need the slots per what? Per pole. Are we having the slots per pole? We do not have. So this is how you connect these formulas, guys. We do not have this. Where do we find it? Is there any information? Do we have the total number of slots? If we have, we just divide. Total number of slots over total number of poles. We have the total number of poles that we have here and also the total number of slots. They're there, this one. So we can divide. 72 divided by what? By 6. You're done. We have the what? The slots per pole. Or you can work it from here. The slots per pole here is there, this one. But we have to get rid of what? Per phase. So it means we can calculate that. Slots per what? Per pole can be calculated. Because we have the slots per pole per phase. So it's 4 times. How do you get rid of per phase? How do you remove this per? To get rid of, you multiply by the number of phases. How many phases do we have? 3. So that was going to give us 12 slots per what? Per pole. Or I said you can calculate it from where? From here. Slots per pole. Slots per pole. Remember, this is what you need. Slots like this. This is what you need. Per pole. So it must be from total this over total this. So we just need what? Total slots over what? Total poles. Just like that. If we can have these guys, we can have per in our question. So what is the total slots? There are 72 of them. What about the total poles? There are 6. So dividing this, we're still gonna have the same answer. That was the idea of your question in this case. All right. So that was gonna give us we said what? 12, is that so? So you're gonna have 12. Meaning to say, in our consideration or in our calculation, the slots per pole, we've got 12, we've got 12 what? 12 slots per pole. So many ways. All right. So guys, just for the sake of revision, I want you to know that you can use any part. So any part. So let me have this. We know that our answer. So let's substitute here. This is where we are here to calculate our angle in this case, which is our slot pitch. So now our slot pitch can be calculated 180 electrical degrees over what? The slots per pole, which is 12. So that was going to give us 180 divided by 12. All right, let's just use our calculator here. 180 divided by 12, which is what? Which is 15. So that's 15 degrees. So we're going to obtain 15 electrical degrees. All right. So let us take it back now. Let us take it back because we now have our slot pitch. All right. Our slot pitch is there. So let's bring it back to the what? To the angle of shortcut. Or so to this KD. Remember, guys, you see my board? Where how it is here. Let me do like this. Here to the KD. Distribution factor can now be determined. This is how we're gonna connect our formulas, guys. No way, no way. There is no way you need to connect your formulas. So our KD can be calculated from there. The sign of what? Any, remember we have them, the number of slots per pole, all of them, they are there. So it's any, sorry, let's substitute our N is what? 4 times our slot pitch, which is what? 15 electrical degrees. So that's 15 degrees there over what? Over 2. And this is over what? The same n, this one, which is 4, the sine of 15 degrees over 2. Now I'm very sure that I did a similar question like this. I'm very sure about this one. But it was like other values, like the other values, but the other statement totally different. They do something like that. They just want you to figure out how to answer these questions, guys. All right. So your KD was going to give us, it was going to be 0.958 like this, meaning to say we have our KD. Like I said, we need to calculate KP, our pitch factor, distribution factor, and reverse up to the what? Up to the question. So how are we going to reverse? With these values that we just calculated, all right? Let me erase, guys. Like I said, as for me, guys, as for me, you must forgive me. There's no way, guys. I have to erase some of this so that we can complete this class. Otherwise, we might not. So here we are. We are now reversing. We needed this to calculate what? TP. So now TP can be calculated. So therefore, TP, you write your formula. This is the formula for TP. So I'm not going to rewrite, guys. You just rewrite your formula there. So that's EP. We have our EP. Remember the phase value, our induced EMF per phase. So that's 1905. Reversing this, guys, there is no way because these values, they were missing. So you calculated them. So as you are reversing, it means they are now there. So it will be just substituting like that. It will be flowing. It will be just flowing. So let's write times frequency. Our frequency is there. Our frequency is what? Our frequency is 50 hertz as we are given there on our information there on the table there. Frequency is what? It was 50 hertz. All right. Our useful flux, we are also given 55 milliwebers, 55 times 10 to the exponent of -3. Our KF, 1,11. If we are not given, you use this one, 1,11, unless stated otherwise. So you've got your form factor there. You move on to the pitch factor. You calculated this. These are the ones that we needed. So we have this one. All right. Just going to substitute. That's 0,966 times what? Our distribution factor, in this case, which is what? 0,958 like that. Substituting this was going to give us the tens per what? Per phase. So we have the tens per what? Per phase, which was going to be 168,615, something like that. So we have this as what? Our tens per phase, per phase. Where is it needed? Remember, it's a reverse now. The tens per phase were needed where? Here. On the calculation of what? Our ZP. Conductors per phase. So therefore, our conductors per phase ZP was going to be calculated because we have got our TP. So we're just reversing now, guys. It will be like that. So you see now it will be just flowing. So that's 2 times what? Our TP, 168.615. You substitute, just like fault finding, you are in industry, fault finding. Find this, you see this one is missing, you work with this one. It's just like that. They want to train you guys to be good at that. So this one is going to be 337.23. That is what we're going to have. Remember, these are conductors per what? Per phase. All right. Very sorry. Just hope it's not going to affect conductors per what? Per phase. Right. Let me just write in short. All right. Sorry for this. I knew it. I knew it. I knew it. So, like I was saying, guys, these things they happen. So we have got these are the conductors, but they are per what? Per phase. So I'm just gonna write conductors per phase. All right. Remember, it just I see these softwares, guys. Meaning they do not want us to work with these major subject, these subjects where you have got a lot of things. So what can we do, guys? Tell me, guys. We have to join membership so that at least we can try to figure out ways. But still, guys, it does not even work. So this is it. We have the conductors per phase, which was needed where on calculating of the Z total here, total conductors. Because we said with this, we can calculate our Z total. Remember, we're just reversing. So from this one, we go to the what? Z total. So we're just going like that, going like that, going like that, like that, like that, like that. So if it is like that, guys, you saw what happened. So I'm forced to be now erasing these because of that. So we can calculate our Z total here. So our Z total, you take your formula as it is, right? So our ZP is there, 337.23 times what? Number of phases. Remember, we are dealing with a three phase. It's a three phase that we are working with. So you're going to write the formula, then you substitute your values. So that was going to give us 1011.69. We are dealing with total conductors in this case. Not conductors per watt. The number of conductors is they are. There is no pair there. Which is needed? Where do we need this? Remember, the total here is the one that we need on our major formula here. All right, our major formula. The question, calculating of conductors per watt, per slot. So that is how you reverse, guys. You just have to be careful in your presentation, just like that. You reverse everything until you get to the what? To the question. Your question was conductors per slot. Now we have got that total. So you're going to substitute. So therefore, the conductors per what? Per slot. Yeah, I don't know, guys, about this. But it's just the T. I don't know how am I putting the T there. So we have got our total number of conductors, 1011.69 conductors over the number of slots. How many? The total slots. We calculated this. It was what? 72. So we calculated that's 72. So dividing this, it was going to give us 14.0512, something like that. That's how you find out these values, guys. You work out that way. Present your information, your formulas. Fill in what is missing. From what is missing, you see this one is missing. Find what is missing from what is missing until you get to the final step. And since these are conductors per slot, we can approximate this to the nearest whole number, which is 14. That's a 0 there. So just approximate to the nearest whole number. So that's 14 conductors per what? 14 conductors per slot. That is the question. Just like that. So using this information, guys, let us attempt other questions. Try. There's also a typical one, April 2016. So I want you to go through that one, April 2016, similar to this one, so that you see how these questions are given. We are on the EMF equation. The first part, they can even ask a question from there. So you see, it is important to know your basics. All these basics, they're important. So I need you to go through that and other questions, but we shall meet again, guys, working with question papers. We shall meet again.